Good day. Now we will be answering problems from Chapter 23, Electric Potential. We will answer problem numbers 23.53, 23.57, and 23.68. So let's start with the first problem, problem 23.53. A particle with charge positive 7.6 nanocoulomb is in a uniform electric field directed to the left. Another force in addition to the electric force acts on the particle. So when it is released from rest, it moves to the right. So from this point up to this point. After it has moved 8 centimeters, the additional force has done 6.5 times 10 to the negative 5 joules of work. The particle has 4.35 times 10 to the negative 5 joules of kinetic energy. Part A, what work was done by the electric force? Part B, what is the potential of the starting point with respect to the end point? And C, what is the magnitude of the electric field? So to answer the first question, we will use work energy theorem, which is total work is equal to the change in kinetic energy. So the kinetic energy final minus kinetic energy initial. Since the initial condition is the particle is at rest, then our initial kinetic energy is 0 because the velocity is 0. Since Kb is given, 4.35 times 10 to the negative 5 joules, we will left with total work is equal to 4.35 times 10 to the negative 5 joules. Since the electric force Fe and the additional force F both do work, then the total work is the sum of the work done by the electric force and the additional force. So there are two forces acting on the particle. Now, to get the electric force, we will rearrange this equation and we have work done by the electric force is equal to the total work minus the work done by the additional force. Substituting the values, so we have solved this one, the total work, and the force, the work done by the additional force given, we will have negative 2.15 times 10 to the negative 5 joules. So this is the work done by the electric force. For the potential of the starting point with respect to end point, we will use this formula. Work from A to B is equal to the negative change in potential energy. So we know that potential energy is equal to the product of the charge multiplied by the potential. So giving us this. Work from A to B is equal to Q quantity potential A minus potential B. Rearranging this equation to get this potential, so we have potential A minus potential B is equal to work from A to B over the charge. Substituting the values, so this is the work and this is our charge, giving us negative 2.83 times 10 to the 3 volts. Now let's calculate the magnitude of the electric field. Since E, or the electric field, is uniform and directed opposite to D, so our D is to the right, our E is to the left, then we have work from A to B is equal to negative electric force distance is equal to negative QED, because we know that electric force is equal to QE. Rearranging to get the electric field, we have negative work from A to B over QD. Substituting the values, so the work from A to B is equal to this. So VA minus PV. And the Q will be cancelled when we substitute this value to this, leaving us potential A minus potential V over D, and it is negative. Substituting the values, we have negative, negative, 2.83 times 10 to the 3 volts over 0.08 meters, giving us this answer, 3.54 times 10 to the 4 volts per meter. Now, let's have the next problem. Problem 23.57, an ionic crystal. As shown in this figure, there are 8 point charges, 1, 2, 3, 4, 5, 6, 7, 8, arranged at the corners of a cube with sides length d. So this is the side length d. The values of the charges are positive q and negative q. This is a model of one cell of a cubic ionic crystal. In sodium chloride or table salt, for instance, the positive ions are sodium ion and the negative ions are the chlorine ions. Calculate the potential energy U of this arrangement. Take as zero the potential energy of 8 charges when they are infinitely far apart. B. In part A, you should have found that potential energy is less than 0. Explain the relationship between this result and the observation that such ionic crystals exist in nature. So we have here the Coulomb's constant. Since there are 8 charges, then there are 28 pairs. Let's have the breakdown of these 28 pairs. There are 12 opposite charges of separation distance d. So shown in this figure, this negative q and positive q are opposite charges with separation distance d. If you count them all, there are 12 opposite charges with separation distance d. Next, we have 12 equal charges of separation distance of square root of 2d. So in this figure, we have equal charges, and we know that in a square, which is the face of our cube, geometrically, the diagonal is equal to the square root of 2d. And lastly, there are 4 opposite charges with a separation distance of square root of 3d. Geometrically, inside a cube, the diagonal is equal to square root of 3d. And this is the separation distance between the opposite charges, or in this instance, positive q and negative q. Now, to answer the problem, we will use the potential energy formula. So, K multiplied by the product of the two charges over the separation distance R. So, we will get the summation of all the potential energy of the pairs. So, to get that, we will substitute the value. Since the two charges are of the same charge, so we have Q squared here, and we will substitute the separation distance R. So, for opposite charges, we have negative. For equal charges, we have positive. And again, for opposite charges, we have negative. Simplifying this, we have this 1. And solving this part, we have 0.485. Now, we will use the expanded form of our Coulomb's constant K. So, K is equal to 1 over 4 pi epsilon naught. So, here it is. And solving this, we will get negative 1.46 q squared over pi epsilon d. So this is the potential energy of the arrangement. In part B, the electric potential energy is less than 0. So obviously it is negative 1.46 q squared over pi epsilon naught d. Then it is energetically favorable for the crystal ions to be together or to exist in nature. So let us have the last problem, problem 23.68. A thin insulating rod is bent into a semicircular arc of radius A, and a total electric charge Q is distributed uniformly along the rod. Calculate the potential at the center of curvature of the arc if the potential is assumed to be 0 at infinity. So to solve this problem, we will use calculus. But before that, we know that the circumference of a circle is 2 pi r. Since we only have semicircle, we will divide this by 2 and we will get pi r as the circumference of our semicircle. Now let's proceed. We will divide this rod into infinitesimal segments dq with an angle d theta. So we know that dq is equal to the linear charge dl, with the linear charge is equal to the total charge of the rod divided by the circumference of the semicircle, and dl is equal to the product of the radius a multiplied by the d theta, or the angle of the segment. The potential dv due to dq is given by this. dv is equal to 1 over 4 pi epsilon naught dq over r. This dq, we will substitute it with this value, lambda dl. And we will substitute lambda with q over a. So here it is. Simplifying this by substituting dl with a d theta, we will have 1 over 4 pi epsilon naught q d theta over pi a. Integrating this to get the total potential, we have v is equal to 1 over 4 pi epsilon naught integral of q d theta over pi a from 0 to pi. Getting the integral, so we can take out q over pi a since they are constant, and we will be left with the integral of d theta from 0 to pi. Calculating the integral of d theta, we have theta, and evaluating it from 0 to pi, we will have phi minus 0. So since we have pi here and pi below, we can cancel this 2, and we will left with 1 over 4 pi epsilon naught q over a.